Today, we're delighted to have two of our Corwin mathematics authors. They are the authors of the Figuring Out Fluency series. And for a nice surprise to start your week, Corwin will be giving away 2 books at the end of the webinar to 2 random winners. So stick around and see if you're one of those lucky winners. And now I have the pleasure of introducing today's presenters. Next slide. Jennifer Bay Williams is a professor of mathematics education at the University of Louisville, where she works with pre-service and practicing pre-K through 12 teachers. She has also taught kindergarten through 12th grade in the United States as well as Peru. She has authored numerous books, all of which focus on developing aspects of effective mathematics teaching and learning. And joining Jenny is John SanGiovanni, who is a mathematics supervisor in Howard County, Maryland. There, he leads mathematics curriculum development, digital learning, assessment, and professional development. John is an adjunct professor and coordinator of the Elementary Mathematics Instructional Leadership Graduate Program at McDaniel College. He is also the author of numerous books. This webinar will focus on their Fluency series, which includes the anchor book, Figuring Out Fluency in Mathematics Teaching and Learning, as well as its 5 classroom companions. And now I will turn it over to Jenny and John.
Well, thank you for joining us tonight. I'm happy to be co-presenting with John, as always. John?
Yeah. Hello, folks. Welcome. Thanks for spending some time with us tonight. And you're right, Jenny, I'm looking forward to spending some time with you as well.
So John and I actually spent much of COVID together working on this book series. So just for context, the rainbow one is what we call the anchor book. And it has the big ideas, many of which we're sharing tonight. And then the classroom companions are full of activities to help supplement whatever curriculum you have in order to help students learn to use strategies and then learn to choose strategies. And each book has a different content focus. So this blue book that came out last week is on middle school topics. And the first book that came out is the golden book that's on addition and subtraction of whole numbers, and then on up through fluency across the grades. So just for context. And that's why we're smiling, because they're all out.
Yeah, and I had a full head of hair.
We're super excited about it.
Right. I had a full head of hair before this whole thing started, so that's all I got to say. But anyhow, go ahead, Jenny. What do you want to say?
Okay. Meanwhile, we wanted to kick off by asking you to share your expertise. There's many of you here tonight live, so share something, either A, which means your entry in the chat will start with the letter A, so something you have figured out in your
professional
journey, or B, something you're trying to figure out.
Yeah, Jenny, we'll check that out for a few minutes and see what pops in there. I kicked this off. I had to. Oh, some good ones off to get there, Jenny. Fluency is not just speed. A couple of those C, cooperative learning. Nancy, you're not playing by the rules. Fluency is not memorization, Kathleen. It's a good one there as well, right? We talk about,
I love seeing the A, no time tests.
I saw that one as well.
That one could come back through. Just keep scrolling it through.
I also saw that one about B. Oh, how does automaticity relate to fluency? That's a pretty awesome one as well. Some really nice, good questions in there. I saw a question about fluency in middle school. Did you see anything else that popped to you, Jenny?
I can't read this fast.
Oh my God. Well, clearly
fluency in reading also doesn't have to do with speed. So hopefully, Margaret, you might scan these great letter Bs for some things that we talk about at the end. There's some really, I love seeing the word flexibility. I'm seeing that word fly by, and that's really key to the things that we're talking about. Yeah, so keep the ideas coming. And if you do have something that you're trying to figure out or that you want to talk to about at the end, remember, add it in the chat. And if John and I don't see it right in the moment, then we will definitely, Margaret's trying to help us find those so we can come back to them at the end. We are going to take on 7 big ideas about fluency. And John's up first with big idea number 1.
That's right. Big idea number one, maybe captured a couple times in the chat box in some way, Jenny. Fluency isn't basic. And that's a really, that's a really big idea. Let me jump into it. Let's do some math together. What do you think? So if you could, wherever you are, your desk, your chair, your couch, your bar stool, take a moment to find the sum of 49 plus 27. Don't share it with anybody just yet. All right. So first, I hope we all agree it's 76. Because if we don't, this is a totally different session that Jenny and I are not prepared for. So we're all good with 76. Now, I am going to ask you to, if you're interested, and I'd love to see it, how did you think about 49 plus 27? So again, it's a chat box one last time. Record it as best you can. We're not going to, oh, look at those popped up right away. So we have some 50s plus 26s. I noticed a couple of those. I saw 50 plus 27 and then take one away, which is similar but different. I saw another compensation of a 50 plus 30 and then take 4 away, right? I saw 80 minus 4, which builds on that idea. Some others said they thought about the standard algorithm in their head, which is fine too. I see 50 plus 26. Oh yeah, you got all kinds. Oh, 60 plus 16, building off the idea of decomposing by 40 or by place value, think about 40 plus 20 and then 9 plus 7. Sometimes students might think about 49 plus 10 plus 10 plus 7, right? Actually, I saw one of those just go flying by as well. So we might break apart by place value. We might count on. We saw some compensations. Even that was done in a lot of different ways. So Jenny, if you take us forward, I want to show a couple of kiddos. Years ago, almost 15 years ago, I was interested in looking at second graders and seeing how well they could perform or complete the standard algorithm. And so I was doing the problem 49 plus 27, like the one that you just did. And so I went to one of the little girls and said, tell me how you do this problem. And she said, do you want me to do it like I do it at school or like I do it at home? And I was like, oh, geez, could you surprise me? No, you know what? Show me both. And she did. In fact, you could see her work right there. She was able to do math like she did at school, 49 plus 27 using a standard algorithm. But then at home, she thought about it as, well, 60 and 16, and she put that back together again. And you should keep in mind, this was years before the Common Core came out, and those strategies and alternative strategies and things had been talked about in pockets of the country. It wasn't really a mainstream instructional approach. So I started asking more students the same question. I said, can you show me 2 different ways to do math or to do the problem? And here's another student who thought about 49 plus 27. Yes, most of them could do the algorithm, but then many others were talking about other ways to manipulate it. So 49 plus 7 is 56, and they counted on from there. We see some ideas of students who did some adjusting. We see some partial sums, and well, you get the idea. And then there's one more student I want to lift up for you. And this is a student who had the algorithm down, right? But maybe not the understanding. This individual knew their facts. And in fact, when I showed the student work to his teacher, she was surprised because he was one of the first to know all of his facts. And if you notice, 9 plus 7, 16, I put the 1 up there, 4 plus 2 is 6. Oh, what do I do with the 1? Oh, I bring it down. I've heard that somewhere. And though a procedure was memorized, not only was there an understanding, but we might argue there wasn't any fluency, which brings us to this notion that fluency isn't basic. If you think about fluency, there's a grand scheme of fluency, procedural fluency. For a middle school chat box, like, I don't know, the way we work with functions and algebra, those are fluent behaviors. There's computational fluency, which we just experienced. But for many colleagues, fluency is nothing more than basic facts, or at least that becomes the anchor for what is fluency. And it's a misconception. Fluency is so much more than fact recall. In 2001, the National Research Council defined fluency through efficiency, flexibility, and accuracy. And when Ginny and I were kicking off this project, one of the things that was important to us was thinking about, so what does that look like in a classroom? So when you're solving 49 plus 27, or a student's adding decimals or comparing fractions, what does it mean to be these 3 things? Like, how would we look for that? So one of the things we wanted to kick off with tonight was to calibrate, what do we mean by fluency as we go through the evening? So we created these descriptions or actions, if you will, that you might see in the classroom. What we'd like you to do is just take a moment. You don't have to put anything in the chat box. You want to match some of the indicators or actions on the right with the components. Well, let me give you an example. You see number 2, gets correct answer? That matches with accuracy. Okay. Why? Anyhow, we'll give you just a moment to make some matches, then we'll go forward, okay? I agree. Accuracy is number 2 and number 4. Does anybody see any other connections within there?
It's interesting because we do have a pretty clear conception of what accuracy looks like, and it's more complicated, more abstract to think about what efficiency and flexibility look like.
That's a great point, Jenny. And I think that was one of the things that struck you and me as we had, we started this conversation. When a student is efficient or flexible, efficiency is so often confused with speed, but there's much more to efficiency than just that. In fact, Jenny, if you take us forward, I want to kind of lift up one of our organizers from the anchor book that you shared with others earlier. Now, you're not going to be able to check your right answers necessarily, and some of you might be thinking, oh man, there's overlap? Yeah, we cheated. Well, we didn't cheat, but
we couldn't decide.
We couldn't decide. Well, because trading out or adapting a strategy, like you see in the screen there, is a function of both being flexible, the ability to move between those strategies, but also choosing them or moving out of one to another in order to be efficient, right? And so I think that that's an important thing that's understood, is that these actions themselves are representative of more than potentially one of the components. Accuracy is one that many are familiar with, without a doubt, not just in the audience tonight, but other colleagues and certainly families, right? So, Ginny, any other big ideas you want to share tonight?
There is actually.
Oh, get out of here.
I'm going to move on to big idea number 2, which is that graphic is not complete without reasonableness. So we're going to come back to the same visual. And you see we've layered in a little gray box because reasonableness occurs across the solving of problems, not just at the end, is my answer reasonable? It cuts across. So we're going to return to 49 plus 27. But I'd also like to include an algebra example. So I'd like you to take a moment to look at that problem, because fluency applies across all years, and think about how you might solve the problem that's on the right-hand box.
Well, you didn't say we're doing any algebra tonight. What's up with that?
Don't hang up. We're sort of on two ends of a long journey of working for fluency. So reasonableness begins with this box here, selects an appropriate strategy. So if you think about these two problems and we're working on reasonableness, the question is, what strategies are reasonable to use? So while John said earlier that 49 plus 27, the standard algorithm might be reasonable, what we'd hope is when students are really good at the methods we saw, making 10, compensation, all those ways of thinking mentally, that they wouldn't resort to at least the written recording of the standard algorithm. Eventually, that would be the fluency with that problem. And then I love the ideas that are entering in the chat for the algebraic thinking one. We say in algebra, in the US, jump in people from other countries, but we commonly say the first thing you do is eliminate parentheses. And in this problem, can you see that is not a reasonable first choice? That's not as reasonable as dividing both sides by 5, another option. So just like with computation, there are choices to be made at the first step of solving a problem. So choosing a strategy is the beginning of reasonableness, choosing a reasonable strategy. So then as you're working, remember one of the flexibility pieces is about changing it out. So you just ask yourself, is this going very well? If you're getting hung up or something weird is happening, you're like, that's not reasonable. Something's wrong here. And you go back, right? And you re-examine your work. So that's the middle phase. And then the final phase is that check. Is my answer reasonable? So the student work that John shared is classic example. There's an answer there that is in no way reasonable. Now, some wrong answers are reasonable. So checking for reasonable doesn't always catch those errors. But being able to think, for example, what might the answer be is really important for the 3 parts of reasonableness across the middle. And then part of jump in, John.
Well, no, I think you're about to talk about it. But the other thing is, if you could go back one slide, sometimes you just see stuff, and it popped up in the chat box, and for others, maybe it didn't because of the way that we were taught to do math or required to do math. But I see a basic fact there, which means I can kind of ignore lots of procedures and just think, well, I'll let you build on that. Sorry.
I love this. In our blue book, we call the method that's shared in the chat called, I know the stuff in the parentheses must equal 5. So I think, so you're using relational thinking is what we call it, that's a method in and of itself. You're just using relationships, your basic facts in order to reason through it without actually doing the divide both sides by something, which is one of 4 possible transformations that are part of the choices you have when you're solving an algebraic equation for a missing value. So more on that in book 5. No more on that tonight, though. But on reasonableness, back to reasonableness, part of reasonableness is my answer close to what I anticipated it to be? So estimation, we're not doing a big thing on estimation tonight, but it's really important that estimation is part of reasonableness, but reasonableness is sort of this bigger piece. So we wanted to share with you a couple of routines that are great for working on this reasonableness, which is this estimation, so that they can decide if their answer really is reasonable. So it's this first one is called over under. And this is the way that it works, is you share an over under number. So be thinking about your grade, your content course, of some math, some procedure that you're working on. And then you're thinking of an over under number. You're going to pose each expression, one at a time, asking students to respond, is it over or under? Provide think time. That's key to all good routines, is the think time. And then people share. All right. I wanted to do something with negative numbers because, again, fluency goes up through the grade. So here we go. The number that we're going to do over or under with is 0. This really helps students when they're working with positive and negative numbers and subtraction to understand what direction they're going, which is usually the most common mistake that is made. So you can type in the chat, or you can just say to the screen your answer. You can type in an O for over and a U for under. Okay, and the second one. I'm seeing lots of O's in the chat. If you're listening to the recording and don't see the chat. And now I'm seeing a lot of U's. And you can see, if you've taught this topic in the curriculum, you know some of the mistakes students make is not knowing what sign they have because they're following some kind of procedures that don't make sense. So this is really helping them build their number sense. And then you go through like a list of 4, and that's how that routine ends. But of course, we can do this routine for any number topics, right, John?
Yeah, totally. So if you teach second grade, a great chance to practice over under with 50.
And if you're working, if you're working with, And fractions. Fractions is where we really start to get into where there's some really wacky answers that don't make any sense. So it's a great other opportunity for over under.
Yeah, and Jenny, as you stay there for just a second, actually go back for just a moment, right? If you think about over under 50, well, that's perfect for second grade or third grade. I'd argue we might have some fifth or sixth graders that need that practice before they then get into fraction work. And if you look at the screen for a moment, we see 29 plus 19 with a decimal point placed in there, and you had 2 and 9/10 plus 1 and 9/10. It's a whole new routine with another number type. And that's something that's really important to keep in mind.
Right. And you can start with a whole number example and then bridge to a fraction or a decimal example. Absolutely appropriate in middle school. All right, big idea 3, here it comes. Strategies are for each and every student. So the most common question I get in my fluency work all over the place is, isn't it just too much for students who struggle to, it's enough for them to get one strategy down? Isn't it exasperating their challenges when we ask for more than one way? It's a big equity issue. And so here are the reasons, not, the sort of reasons people think this statement might not be true. They'll get confused. They don't need all the strategies. Isn't the point to learn the standard algorithm? Isn't the right answer all that matters? And there's too many strategies. So John and I just want to kind of take this on really quickly. And so first of all, why one way isn't best for any student? The numbers change. No one strategy is the best strategy for the numbers. Situations change. So as they mature, other strategies become more reasonable to use. And then you have this individual difference, as you saw when you all answered this problem, 49 plus 27. You have different ways that you lean on, but you actually do have some choices to make. So you have access to those choices. So for me, this boils down to what instructions are we giving when we give tasks? So for example, right here are 2 lists I love to share. Solve using any strategy. So I've got one on the left with subtraction and one on the right with proportions. Once again, a topic where both of these topics where we sometimes say, this is the way you solve this. So I'm going to lay out the whys for why we're going to teach every student more than one way. So my first why relates to this list. If you look down this list for a moment, let's just look at number 1 on proportions. The butterfly method, as it's dreadfully called, leaves no number sense. Implemented here is a mess. All you need to do is notice that the denominator over here on the fraction is twice the numerator and use that relationship to figure out what n is. And in the same way, there's all kinds of reasoning strategies that are more efficient. Remember that visual fluency for these. So if you solve using any strategy, as compared to telling them which strategy to use, like solve using partial sums or partial differences in this case, or solve using the butterfly method, then you open up an opportunity to talk about their reasoning. So reason number 1 is that when you have more than one way, you have opportunities for the math practices to develop. They're looking at structure, they're using their reasoning, they're justifying their thinking, they're critiquing other people's reasoning. Number 2, strategies are number-based. They make more sense than our algorithms that are digit-based. As a comparison, strategies are, work with the larger place values first, and there's flexible options, not just an established set of steps. Number 3, strategies often require fewer steps. The definition of efficiency that John and I have in our big book is that a strategy is considered appropriate. Sorry, it's our definition of appropriate if it's about as efficient as any other of the options. So when it's really a lot longer and more involved than others, then it's not a good choice. So this would be an example right here from the subtraction list, where it's not appropriate to use the standard algorithm here. It actually takes longer to rewrite this problem than to solve it. That's not even the solving of it, right? If you set it back up. And number 4, as we already shared, knowing one more is necessary for fluency. You can't choose an appropriate method if you don't have any choices. If you only have one choice, it's not a choice. So that gets at the why. And so the stress quote that you saw around, there's so many strategies, there really aren't. So I'm moving over to the what. What are the really important strategies? So for example, for addition and subtraction, the focus of the companion books you see are these 5. These are useful strategies. Are they the only ones? No, but they are so useful. They're useful because they work with whole numbers, they work with decimals, they work with fractions, they work with negative numbers. These strategies have big payoffs later on. And by the way, they begin with basic facts. For multiplication and division, here's the list. Notice we have compensation back again and partials back again. And this is the list for all of them. And again, we grow them from basic facts all the way up through middle school rational number work. And then beyond the operations, we've been working on what are reasonable strategies for the other things. And so this is just a quick look. We're not going to spend much time on here, but for comparing ratios, here's some good strategies. I spoke earlier about the options for solving equations for an unknown. Use relational reasoning or choose one of these moves, one of these transformations. And then, of course, solving systems. Instead of telling students, solve using substitution, look at the 2 equations and decide how you're going to solve them. John and I believe that the reason people think there's too many strategies is because there's confusion around the difference between a representation and a strategy. So I'm going to ask you to type in the chat an R if what the student says is a representation and an S if you think it's a strategy. You ready? Tara, an R for representation or an S for strategy? Okay, how about Oscar? Oscar's using a representation. Yeah, I know I'm going super fast.
I was going to say, we just destroyed the chat box.
John and I have a side bet going here. If my part's going to be over by 7, that's our side question. I looked at a 100 chart. Yeah, where are you seeing? That's a representation. We don't know how she thought about the hundreds chart, so we don't know her strategy, how she used it. Devonte, sharing a strategy. Kendra, a strategy. Jorge, a strategy. Tina, a representation. So we can help students by making this very visible, like an interactive bulletin board, where as we teach a strategy and we use representations, we put them up there. Then we provide a visible menu, making the strategies and the tools they can use to help think through the strategies visible to students. So here's one called subtraction actions, or you could do actions for comparing fractions. And those are all ideas so that these multiple strategies can be accessible to all students. To you, John.
Go back for just a second, Jenny.
Oh, no,
and note the time. But I think this is really important for us to recognize, and that is that it does feel like there are hundreds of strategies or countless strategies. We don't recognize that how we show our thinking is not the actual thinking. The strategy is the thinking. It's not just about computation, but so much more of mathematics that is part of that as well, right? So I think that's one that builds toward the rhetoric of there's too much, they'll get confused when really there are only those 5. That being said, take us forward. Because it dovetails perfectly with this next idea. I mean, the big idea here is that we have to take time to teach, practice, and assess strategy as well. And nobody's going to argue that. And we focus a lot of time on teaching and assessing, as we should. But Jenny and I thought it'd be important just to double click on practice for a few moments, right? Because practice sometimes, at least the experience that I had as a child, and maybe others in this room have as well, is that, more practice is better practice. And well, that narrative might need to change. In fact, fluency practice is probably something like this. It's coming. There we go. Well, it's not really, probably something like this. So we know that high quality fluency practice takes on a couple of different components. It's focused, and we're going to take a look in just a moment at what we mean by focused, but it focuses on a strategy one at a time before it builds from there. It's varied in that we practice driving cars and hitting golf balls in lots of different ways, right? And so the same idea here is that practicing fluency in varied situations is important. Helping students see connections. And Jeannie and I were thinking about how could we lift up seeing a focus and a connection at the same time. We thought we did a nice job here in just a moment. I'll show you in a moment. And then last but not least, the idea that after practice, something as a teacher I needed to work more on, and that was helping students process, like, what did we just do and why did it matter, right? So Jenny, take us forward to a game that we wanted to lift up tonight. This is a game called A Winning Streak, and it's one of my favorite games. The idea here is that you have two players that are rolling 10-sided dice or flipping over digit cards, and they're focused on making a 10. If you notice, it says plus 19. Imagine it's second or third grade or something like that. And what happens is students will roll a number and add it to 19. So the first player rolled a 4 and decided to put they made 20 and had 3 left over, so they had 23, and they placed their counter on 23. And you're like, well, why'd they put it on that 23? Well, they can pick on either 23s, but they can't cover them all at the same time. Then the next player rolled a 7 or flipped over a 7, however you want to think about it. And they thought about 7 and 19. Well, 1 and 19 is 20. There's 6 left over. So they then put their counter on 26. And then the next player, it was back to player 1's turn. They picked a 5 and rolled a 5. And 1 makes 20 and 4 were left over. So they placed theirs on 24. And so students keep taking turns. Now, imagine this game right now, plus 19 playing out in the first grade classroom, right? But then imagine next week or the week after, it's plus 29. And instead of seeing numbers in the 20s in there, you see numbers in the 30s. And then maybe 2 weeks after that, playing plus 39 or plus 49. And then imagine 6-year-olds saying things like, Mr. S, this is the same thing. Each time you're just making a new 10 and then you have some left over. In fact, Jenny, if you take us forward, that's one of the things we wanted to lift up. Notice that each of these are focusing on the notion of making a 10, right? But the idea of making a 10 goes well beyond, well, first and second grade. I mean, it dabbles into ideas of making a 10, adding it to 649. And then ultimately you make a whole when you add something or tenths to 2 and 9/10 or to 3 and 9/10. You can see that on the right side of your screen. But now imagine a 5th grader who plays just for a moment, add to 29, and then has to pivot and play add to 2 and 9/10. Now, we once thought, yeah, you got it, Jenny. Thank you. I wasn't ready for you. You got me on a premature click there. Anyhow, we once thought good practice was more practice. In fact, we once thought like 40 problems on a piece of paper was good practice. And well, today we know that probably isn't good practice for lots of reasons. One, and the one that I hang my hat on is, that's how little girls and boys fall out of love with math. Nothing says, why am I doing this, like 40 problems on a piece of paper? But along the same lines, we also know that repetitive practice like the one you see on your screen leads to diminished flexibility and reflective thought, things that are part of what it means to be fluent. It actually undercuts number sense and reasoning. And that's not what it means to do math. And that's the important thing. Math is so much more beautiful and dynamic than what you see on the screen. And that's not to say we should never do math on paper. But what if we change what you see on the screen to be better practice? Jenny's chatting and clicking at the same time. Apparently she's doing more chat than click. Hook me up, Jenny.
I'm not a good driver.
I'm running out of spiel here. So what if we took a traditional practice set like the one you see on the left? And that's not to say a couple problems on paper to find the sum. Accuracy is part of fluency, right? But what if we change the question to be something like, circle the problems that would be good to solve with a make 10 strategy? And now we're focusing on flexibility. Or what if we change practice to be something else, such as find 3 problems that would be good to solve with counting on? Or what if we developed reasonableness? What if we said something like, circle the problems that you estimate to be more than 100? Because one of the things that we don't always do a lot of, or at least I didn't do enough of, was practicing estimation in these kinds of settings. And then look at the last one, which will lead us to a big idea in a few minutes. Circle 5 problems you can solve without an algorithm. Because there are problems that students are forced to solve with an algorithm, like 99 plus 3, that really aren't algorithmic problems.
So it's important to practice strategies. One thing I think, John, that is really important around strategies that we will come back to is really the game that was shared is an opportunity to practice and practice and practice one strategy. And then as they move to that quality practice worksheet, then they're getting a chance to choose when they want to use that strategy. And so they become adept. And those are all stepping stones to really being that fluent person. So we're on big idea number 5, which is strategies grow up. So I would like to take us back to basic facts and share a common thing that's taught when we teach, like the making 10 strategy, which is to show a quick look. It goes up once, you hide it, goes up a second time, hide it, goes up the third time, and students share how many and how they thought about it. So this is just sort of a finished product here where they might think about it by moving 2 over to make a 10, or they might actually pretend that this thing was full. So they might add them and then subtract 2 from the final. So, but right now I'm just focusing on one strategy, making 10. And you oftentimes will hear people say, well, why don't you just remember that fact? 8 and 6 is 10. Why don't you memorize it? Well, there's a lot lost when students don't actually learn the strategy because the strategy grows. So we're going to water that strategy a little bit. And that's really where the figuring out fluency work takes off. We do a tiny bit with basic facts, but John and I have done other books on basic facts. This is growing it out. So for just this one strategy, it grows from this idea of 8 plus 6 equals 14 to this idea of 39 plus 28. After they've played the game that John just shared, they start developing this idea they can move some over to the 39 to make a 40. And then, of course, that applies to hundreds, but it doesn't stop there. It goes to decimals and fractions. And so we can now make a whole with our decimals, moving some over. I feel like even if we're trying to make our attempts at flexibility and strategies with whole numbers, when we get to decimals and fractions, we're back to our algorithmic ways of being. And so this is a powerful strategy that works with decimals and with fractions. Think about 3 3/4 plus 2 1/2. How much easier it is to rethink it as 4 plus 2 1/4 by moving a 4th over, which of course requires this automaticity around fraction equivalencies, right? So there's some background knowledge that's needed to do that. And then let's not stop there. Let's go to our integers. So you saw this a little bit in the over-under idea, is how do you navigate integers? And one way would be to break apart the number that has the larger absolute value and to match the other number. So you can see how that's playing out here with 15 and negative 15 to make a 0. And then you can see what remains as a strategy for working with integers. So we start with basic facts and we grow that strategy. And because it's so useful across all numbers. John, you got something else to share?
Yeah, I do. Big idea number 6, which, well, comes right before 7. I was saying that because I was in the middle of answering a chat. You got me off the mark. I'll come back to that chat question there in a second, Lori. But so here's another one that's a big one. And an algorithm is not the end goal. Sometimes the way our curriculum is written, right, no matter where you may be, algorithms appear later in the sequence of instruction or at the end of the set, or, there is one standard set for algorithms specifically. And it insinuates, or we're led to believe that the algorithms are the end goals of mathematics instruction or fluency instruction, right? So Jenny, pop up those problems for me again. And take a moment as an adult to solve a couple of those and think about, like, which ones would you use an algorithm for? Nothing you have to put in the chat box. Just think to yourself for a moment. Like, which of these would you solve with an algorithm? Years of experience and you see 25 minus 19, you just think 6, right? But in other situations, you may not line things up, subtracting or group, and you're finding equivalent proportions. You might use other strategies and cross multiply and divide, right? Because being fluent is not about skill with an algorithm. In fact, one of the things we need to work with our students, I believe, is helping them think about, when do I need an algorithm and when don't I? When do I need a list of steps and when can I manipulate numbers? In fact, Jenny, will you take me to that next student? That's a real student who once told me the answer was 102 before she had to do it on paper. She saw the problem 99 plus 3 and told me the answer, the sum, was 102. And when I left her to go visit other students, I came back to her, and that's exactly what was on her paper. When I asked her why she did that, she said, because that's how you have to do math. So one of the other routines that we want to leave you with tonight is called that one. It's one of my personal favorites. The directions look a little bit like this. You pose 3 or 4 expressions to students, some that lend themselves to expressions and some that may not. Then you have students find the ones where they would use an algorithm to solve, or a calculator, and then those that they could will solve mentally or think about and manipulate and use a strategy to solve. Then they turn and talk with the partner and you have a discussion. Actually, let's try that with an adult version or a middle school version. Like, what is the one on the screen right now? What's one that you would definitely solve with an algorithm? And what's one that you might mentally find or use a strategy to solve?
By the way, if you're thinking I wouldn't use an algorithm, I'd use a calculator. We agree that D might be a calculator problem, but we took calculator off that when you're deciding how you're going to use it when you don't have your phone with you or your calculator, that's not one of the choices.
Right. That's a good point. That's a very good point, Jenny. That's a really good point. But when you look at some of those, you think about them and you might think like A is one that I don't necessarily need an algorithm for, because I can think about 2500s being 1/4. And so therefore 1/4 of 48 might be 12, right? Or maybe B, you thought about decomposing 12 and 2/10 into 12 and 2/10, finding partial products. Or maybe you thought about F doing the same thing. Or you just knew that double 4 and 5/10 was 9. Anyhow, the moral of the story is simply this, that one of the things we can do to realize fluency is helping students think about situations that would be ideal for maybe an algorithm, or maybe not. More importantly, the ones that aren't. What's it look like across grades? Well, looks something like this. Some grade 3 examples on the left side. Working your way across the grade 6 examples. And though those aren't exactly like, you might say, well, that'd be good for my 7th graders. Okay, well, they play in lots of ways. In fact, I know 5th graders who might benefit from like learning how to divorce themselves from paper, pencil, algorithmic math, and might have to practice with number 3 before they can start to work their way to the other examples, right?
That's right. Also, you might be looking at grade 5 and thinking, none of them. I wouldn't use the algorithm for any of them. And that's also a thing I love about this routine is while you might begin with having one that really lends to the standard algorithm and the rest have other shorter methods, having none or having 2 or having 3 makes the routine all the more interesting.
Yeah, that's a great point. And when you look at number 5, Jenny, that's a prime example of rules that we don't understand, why you would flip and multiply. But if you fundamentally understand there's 4/4 and 1, well, you can mentally manipulate that probably pretty quickly. What are some other examples, Jenny?
Oh, I can't find my arrow. Here we go. You mean like these, John?
Yeah, that's exactly what I was thinking about, Jenny. Like those, right? And the idea is that it plays with whole number addition and subtraction, but it also plays well with ideas like these. And though you wouldn't necessarily give students 8, 7 expressions to choose from at one time, we just wanted to kind of give you an idea of the breadth of the examples that you might use with students, and know that we have to honor student thinking, meaning that if they don't identify any of them as ones that they could do mentally or with a strategy that would be evident of fluency, we can understand that. And in later grades, or I should say earlier grades, a conversation might be slightly different. It might be find the ones that you can do mentally. And Jenny, there was one about algebra I think you were going to lift up on 2 slides. You want to show that to us?
Sure. I mean, this routine is so adaptable. So we designed it to focus on identifying where you would use a standard algorithm, because the message then becomes very clear that there's a lot of situations where you don't need it. You have it when you need it, but you don't always need it. And then this is, focused on mental math. When do you want to do it in your head? When do you want to write stuff down? Which writing stuff down doesn't necessarily mean the standard algorithm. And here's another way to use the routine is, how about when would you use compensation? Again, looking for opportunities. Which ones of these lend to compensation? What would you say? If these were numbered 1, 2, 3, 4, for which might you use compensation? You can enter in the chat.
There aren't any numbers. 4. Jennifer nailed it. You're right. I'd think about making that 50 and taking
4
one away.
Could be. Yeah, I see some 2s, which if you're doing 2 by partial sums, it's also a little bit of compensation, right? Because you're sort of compensating. And even the first one could be compensation. So then on the ones where there's mixed reviews, there's some students that raise their hand and some that don't, then that's a beautiful opportunity for them to compare their strategies, which is where that flexibility really comes through. And then, we can do this in algebra or geometry. For which of these would you use the Pythagorean theorem? So just fill in the blank with the strategy that you're interested in working on. For which of these would you use the Pythagorean theorem? And if you're a secondary person, you might recognize the 3, 4, 5 in disguise and some other triangle properties. So you don't really need the Pythagorean theorem for these.
And for our kindergarten teachers, it was okay to play in your
kindergarten teachers were like, what? No. Okay, moving on. So back to you, John.
Well, and just simply, Jenny, the directions for that routine will be in the recording in the slide deck that you have access to. The thing that we want to lift up, one more notion that, remember, practice is varied, right? And so routines are great opportunities. There's paper pencil possibilities. And Jenny will talk about some work examples in a moment, but here's one more game that we want to leave you with. This is one of my favorites. It's called a list of 10. And so what happens is, as a teacher, I would write down a bunch of expressions on index cards or something like that, right? And students take turns flipping over a card and deciding whether or not they would solve that problem with an algorithm or without. And if they decided to solve it without, they would say how they did it without. And the idea is to get 10 you would solve with an algorithm, or 10 that you would solve without, like to fill one of those columns first. There is a twist, though. When I would flip it over and be like, oh, I need an algorithm for this, for 99 plus 3. And Jenny's like, no, you could just count on. It's 102. She can steal that problem and add it to her column. So just one more game to provide you with, because one of the things I've noticed in my work is that we don't have enough opportunities to talk about, is this a good problem for a procedure like that algorithm, or a set of strategies for thinking? Jenny, I think we're down to number 7.
All right. So this has been a theme throughout, I think, the other big ideas. But John and I wanted to finish with this idea because it really is the reason that we wrote the series in the first place, is that fluency decisions have a major impact on equity and access. So we're going to close with this one, and then we'll have some time for questions, I hope. But earlier, I was on a similar topic with why more than one strategy is good for everyone. So I'm just coming back to that why with a finale. Why more than one way? Because it's equitable mathematics instruction is access. If you limit a student's instruction to just one way, they don't get to choose. Then they don't have access to the mathematical practices, to the reasoning, to the choice, to the joy that you get from figuring something out. So it's critical that everyone has that opportunity to really have ways to make sense of the strategies. So like doing the interactive bulletin board, I want to put out another way to help students to make strategies visible. And one of my, there's a lot of research behind this, and I love this practice from like grade 1 all the way up through high school is studying somebody else's work. It's a time saver because they don't have to work the problem. It's anonymous, so it gives a chance to really critique it. And there's, a number of studies about how using worked examples helps students with their fluency and flexibility. So the classic way to go about doing a worked example is they need a chance to consume it. So instead of like having somebody speak at them like I'm speaking to you, you look at it, and then you ask them, first of all, what did this person do? So they can see, well, they pulled an 8th off of that mixed number, and then they moved it over, like we're used to doing with whole numbers. Very interesting, right? Why does this work? And then they can work with a partner, think about it. I mean, this can be a long activity or a quick routine, right? And then the next question after they've discerned why does it work is, when is this strategy a good idea? Beautiful. Then you go back again to a worksheet like John has. Where on this worksheet would this idea of make a whole work out well? Worked examples come in different forms, and they have different purposes. So a correctly worked example is a way to highlight a strategy that students either have never seen before or they don't understand it well, for them to kind of see the thinking behind it. Can use any kind of visuals. A partially worked one would be the same thing you just saw, but it's only the first step. So for example, if we go back, it would just have the very first step where she's decomposed 3 5/8 and then left it for them to finish. Like, now what? So they get a chance to see how it plays out on their own. And then an incorrectly worked example is when you're able to highlight like common mistakes and work on accuracy. So the first two really are working on building up their repertoire, making sense of strategy, so efficiency and flexibility. And the last one's really working on their accuracy. So all the strategies we've shared is really getting at this identity and agency. So when students can make sense of strategies and get to choose among strategies, then they start to see that they themselves are the mathematician. And then when a problem is put in front of them and you're saying to them, how would you like to solve this problem? You're giving their agency a chance to develop. Agency being basically their identity and action. We have so many students that are reluctant to try anything. And this is because they're trying to remember what you told them to do, or the person before you told them to do, or somebody 3 years before told them to do, instead of realizing that those ideas and strategies come from their own mind, their own creativity, and how they do math. John and I say, because effective instruction of real fluency values actions such as selecting, understanding, and evaluating strategies, as well as flexibility and reasonableness, students are able to develop strategic competence and adaptive reasoning. These competencies positively shape their mathematics identity while also nurturing their mathematical identity. We hope that this session has helped you figure out some things about fluency so you can insert an A, or maybe we have said something that provokes new questions for you, in which case you can put a B in the chat. And in a minute, I'll go to a slide that shares the 7 components. So A is something you figured out. B is something that you're continuing to chew on, or you're now going to start chewing on. Here's the list to kind of remind you of this whirlwind tour through big ideas of fluency.
There, Lisa, you got one. A, strategies grow. There's lots of A's in there. I was like, but what was your A? Carrie got an A.
What was it?
Alexis got an A.
Oh, I think they're grading us, or maybe me.
Oh,
they're giving me a grade.
Yeah, that was all the B's. Oh, Elizabeth got an A, and oh, that was good. Strategies grow up, Lindsay. So will I someday, or so Jenny thinks.
I
want to say, you hope I don't grow up, or never mind. Well, folks, we want to say thank you for your time and investing in yourself. We know that back to school is a tiring time for everybody, but we appreciate you spending it with us. We hope we gave you a smile or two and at least something to chew on. And along those lines, if you have any other questions, especially the hard ones, those go to Jenny. Anything else, just fire off to me and I'll be happy to help you out. And I believe there's some other odds and ends to wrap up the evening.
Thank you, everyone.